Yeah, here's your answer for that. And remember that if an object is too big, you won't see noticeable interference effects. And an example of that is everyday scale objects like students, cars, baseballs. And what we'll find when we get up to the end of the semester next week, or actually 2 weeks from now, is that the quantum wavelength of an object like a baseball is so small relative to the size of a baseball or to the size of a hand that catches a baseball that you'll never see interference effects for macroscopic objects, but only for things like electrons. In other words, things that are small enough compared to their wavelength. Okay, next question. Sir Isaac Newton. Now I want you to think about this carefully. What did you say? 15 seconds. Five, four, three, two, one, zero. Um, yeah, the as I mentioned in lecture uh, Monday, the notorious Poisson dot, and I went and reviewed the history of it, and the idea was that a fellow named Fresnel in France proposed a complete theory, a wave theory of light. His comrade Simeon Poisson said, "No way, Jose." And then Professor Arago said, "Yeah, okay, good, but I just actually found it." So here's a picture of our friend Fresnel, pretty young guy in this picture, anyways. Here's Mr. Big Time Simeon Poisson, and here's the guy that put the slap down on Poisson, Francois Arago. He actually found it. So you may find that that whole situation may remind you basically of this. Um, so those guys, in the back of the thing that you guys maybe don't realize is that academic arguments of that nature, like in France, the French Academy and stuff, were they got kind of heated. A lot of drama, I suppose you should say. Anyways, so that's the famous Poisson spot. He's the one that gets the name. I mean, it was discovered by Arago, but they usually call it Poisson's dot. All right, next question. Multiple choice. And this one I want you to think very carefully. We'll go over it in detail. Um, when light goes from one medium to another, the frequency is preserved, but wavelength changes. So my two media are air and water. Easy, we've done them a million times. And those rays of light are tilted accurately. So I didn't draw on the perpendicular, the normal line, but think about what you know about waves and what you know about index of refraction. And I'm going to ask you, if you answer correctly, I'm going to ask you why you answer that. or I'm going to ask you to advance before I show you the correct solution. I'll ask you to advance your answer. Thirty seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. So here's the spread of answers, a few A's, a few B's, and actually 29 people each, and then a few for B. Now B is not correct. There's definitely a change. But what we're going to do now is show you the exact change. All right, so we know this. Go ahead and write this down. The speed of light in medium number 2 is simply the speed of light in a vacuum divided by N2. That's kind of like the definition of index of refraction. Now, N for any material medium is going to be greater than 1. So this quotient is smaller than the speed of light. Speed of light's 3 times 10 to the 8. So this might be like, 2.3 times 10 to the 8 or some other number smaller than 3.00 times 10 to the 8. Right? So there's our first move. Now, C is equal to lambda F no matter what lambda and F you have. Now, up on top, we have lambda 1, the wavelength in air. So I replaced, let me get my cursor over here, this C in the first quotient with lambda 1 F. All right, and I left N2 down here in the denominator. Now over here in medium number 2, now the reason I'm putting lambda 1 F over here is because air is pretty close to the speed of light. It's like you got to go out a few more zeros before you catch any digits other than 0. So we'll just consider that to be the speed of light up here. So lambda 1 F. And then V2, lambda 2 F. Now F is the same for both sides of this equation here. All right, so you can cancel F. All right, so the F's cancel. And what do you have? Lambda 2 equals lambda 1 over N2. All right, so that means now N2 is greater than 1. So you have lambda 1 divided by a number bigger than 1. So lambda 2 is going to be a little bit smaller. Okay. And guess which one that is? Dun, 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 dun. All right. So those of you that answered over there, I don't know if you were doing a coin flip, but this is how you would think it out. Now, I'll just point this out to you. This is a multiple choice question. If you see a problem like this on the next exam, which for us is the final, if you see something like this, think to yourself, do I have to work out a few little equations in the scratch paper area or the margin of the paper like this? This is just a couple little short equations if you know what you're doing. All right. Now remember, as I've mentioned to students in the past and this semester, this class is not about memorization. It's about thinking with the tools that you have at hand. All right. And you'll have tools, you'll have equation and formula tools in the matching. So you do have to know a little bit. You have to be able to recognize, but you don't have to memorize because there'll be, I mean, anything that's on the on equation matching, I never put a false equation. I might not ask you about it. It might be one of the unused options, but it won't be false. So I might put C equals lambda F in a set of 5 equations, and you might need it on the test, but I won't ask you about it as one of the matching items. All right, but it'll be there. So it's like an equation sheet as far as that goes. All right, so that's this problem here. Now, I want to talk about diffraction in general. Now, this is our main topic for today. And while you're changing mental gears, I'll just make an announcement. We're going to have office hours. Bring the lights back up now. We're going to have office hours today, 12:30 to 1:30 in room. We'll do them in my office, PS 156 in the Physical Sciences building. It's right next to the elevator. And if you feel like you want to review your grades and stuff, I cranked out grades for my 2 big online sections yesterday, but I still have to do it for you guys. But if you come in and sit down in my office, we can just, I'll look it up and, we can talk it over. But I think a lot of you know where you stand fairly well going into the final. But if you still have questions, you can ask. Oh, you mean the thing that I made an announcement about? And you, yeah, and you didn't read my reply to the announcement? Okay, there's actually 2 replies in there. Okay, then the question was, what happened to those so-called 3 bonus points from that survey? And the answer is, she was supposed to get me the data on Friday, but I still haven't got it. Something's messed up, but we'll get it. If you took them, you'll get them. Okay, even if it takes us a while. And so I guess you can file, Andrew, you can file that bindle. See, there's Sherlock Holmes there. I'm going to track him down like Sherlock Holmes. Okay. But you can file that bindle of bonus points under bloopers. It's somehow got blooped up, and it'll take a little bit of time. I can't remember your name. Emily. Are you done grading exams? No. So that's still in the pipeline, and you'll get that. So you'll hopefully you get some points out of that. So bonus points are something that if they drop out, if they're not automatic, if they're not graded by Scantron or something or Clicker, it sometimes takes a while. All right. So, but I've got them, and don't worry, they haven't evaporated or anything, and they won't evaporate. You'll get some, hopefully, if you've got anything going for you. All right, diffraction. Here's a generic image, and every graduate quantum mechanics class starts with this experiment. This is the famous 2-slit experiment that Thomas Young actually found and developed and publicized. And he shined a light beam into 2 slits and observed the diffraction pattern. Now, on the second vertical panel there, across the room, is the series of bright and dark bars that form a diffraction pattern. Now, this is a 2-slit diffraction pattern, all right? And it's for 2 openings in a barrier. And the reason that quantum mechanics classes always start with this is because we've known since the time of Thomas Young that light does this. But what we found about 100 years ago, so about 95 years ago, we found out that electrons do this as well. And that's the quantum nature of electrons. So quantum wave theory is encoded nicely with this experiment using electrons. But Thomas Young, the guy in one of the clicker questions, an interesting guy. He did this several different experiments. Very smart guy. You can look him up. Among other things, other than diffraction and the wave theory of light, see, he also was able to decipher the Rosetta Stone, halfway decipher it. And if you remember, the Rosetta Stone is the archaeological fragment that archaeologists found in a place called Rosetta, just a stone out of some Egyptian ruin that they saw Greek Demotic, the Egyptian Demotic language, and then hieroglyphics, which was the priestly alphabet and stuff in the ancient Egyptian empire. And Thomas Young figured out a good portion of the Rosetta Stone, so he was a pretty smart guy. All right, so this is the two-slit experiment. Now, in addition to getting diffraction from light going through openings in a barrier, you can also observe it light going around an object. Now, this is a very, very famous picture from a very, very famous optics book by a guy named Hecht, and the photo by E.H. down there. That's the author of the book making this photo. Those rings that you can see around the shadow of the hand grasping it's a dime. Those rings are diffraction effects. All right, and the helium neon laser beam that he used is visible light. So he got this on black and white ASA 3000 film. Now, if you know anything about photography, you'll know that ASA 3000 is very, very fast. It's very sensitive to light. Sensitive enough that it could pick up diffraction patterns like this. All right. And so last time I told you that you can observe Poisson's spot behind a ball bearing if you use like a helium neon laser like this, and shine it, get everything aligned perfectly and square, and shine it at the ball bearing. You'll see not only diffraction rings around it, but you'll see Poisson's spot if you get it just right. You'll see Poisson's spot behind it. But now we don't have any Poisson spots here, but because for one thing, a dime is not a sphere. And go ahead and make a note. Diffraction around a disk, like a dime, is different from diffraction around a ball bearing, a sphere. It's physically different. So the wavelets behave differently. And you might get a Poisson spot behind the dime, but it'll be different location than behind the same size ball bearing. All right, now we're going to go to the document cam, and we're going to do some double slit diffraction diagrams and sketching and calculations. And from this, we're going to put these up somewhere. We're going to go ahead and switch to document cam. We're going to make a calculation, an example. So I'm going to use two different sketches. Get your calculator out too. You'll need that. And let me get some pencil action here. And here's my pens. Here's my trusty protractor, although I don't really need this protractor today. Okay, double slit. All right, I'm going to orient this way. All right. 11, 20, 19, double slit diffraction. Okay, let's skip out to the right a little bit and draw that first wall in the Thomas Young experiment with a couple gaps in it. Okay, so here's that first wall. And then over here to the left of that, draw some plane waves coming in, evenly spaced, like that. Okay, so here's your plane waves going into the barrier. And I'll do some cross hatching here for the barrier. Okay. Now I want you to draw a symmetry axis here. I'll do it in pencil. Through the middle, right here, this is the center of symmetry of the system right here. So draw, just for bookkeeping purposes, a perpendicular line there. And I'm going to make mine a dashed line. Okay, so there's my symmetry axis. And I'm going to erase a little bit of my symmetry axis and put a squiggle to indicate that I'm going to skip a little bit of my diagram and squeeze down my diagram. And now out here at the far side of the diagram, I'm going to make my my second wall, or my screen, in which I view the pattern of light. Okay, so here's my screen. So that's like the screen of the projector screen, right? You shine. Now the projector's not doing a double slit diffraction, but it is shining onto a screen, and that's what this is. So I'll do cross hatching on here. Okay, so this is the screen. And so you're trying to eyeball that. All right. Now let's label the distance here. Okay, this distance, center of the gap to the center of the gap. Okay. Okay, so here's the lower gap. Center of the lower gap to the center of the upper gap. Let's label that D. Right? And so that could be, you know, like 500 lines per millimeter, like in our diffraction grading. Although our diffraction grading has a lot of different openings, not just two. But, you know, you design this. You know, this is your design factor. Now, what we're going to study here is a bright spot up here. Okay, so there's going to be a bright spot on the screen. Now watch carefully how I draw my following light paths. Okay. Oh, one more thing I have to do here. This is distance L. All right. And we want L to be much, much greater than the slit separation, and we want it also to be much, much larger than the wavelength. Okay, and if that's the case, then you'll have a good diffraction setup. All right, now I want you to go back to the center. Okay, now that's going to be a wavelet source. We'll just think of that as one wavelet source. And I'm going to draw, let's see, I just barely have enough. I'm going to draw a line here from that center point out here. I'm going to make a break, and I'm going to end up here. Okay, so here's my break. All right. Same as my break in this dashed line segment. Okay. And now down here so this is a bright spot. Okay. And down here at this dot down here, just for bookkeeping, draw a line, a dashed line or a dotted line parallel to the main symmetry line. And we'll call that theta. Okay. Now this is the thing that you're going to measure in the lab. In other words, if you know how far away your slits are from your screen, and then you measure this distance up here, this would be like distance h out to your bright spot. All right, you can figure out the trig for that, right? Because you have an angle theta here. You have a baseline. This dotted line you could extend out. That goes all the way distance L. And then you have distance H here. Okay. And so you can figure out all this stuff. All right. So let's call this, we'll call this L2. All right. Now let's go to this one up here. The wavelet source in the upper gap. Now we're not going to draw a line all the way out to the bright spot because we don't have we don't have big enough graph or big enough sketch paper. But I want you to start it out parallel to the L2 line segment. So right about here. Okay. And so this is L1. And we're going to, and I'm just going to ignore the fact that it doesn't aim out there and land at the bright spot. But this is theta 2. This is theta also. So these two angles are theta. Now those two angles are everything. Because at this precise angle, theta, there is a bright spot. Matter of fact, there's a bright spot right down here on the symmetry line as well. And you'll get a countable set of bright spots as you go up. And then you'll get symmetrically bright spots countable going down. Now let's say that this is the third bright spot. Okay, and what we would do, so in other words, there's another one like here, and there's another one here, and then here's the 0th bright spot. The central bright spot, it's like the central image, is the 0th, what we call the 0th bright spot. All right, and so so we're working with the third bright spot. Now, I just wanted to have something fairly far away from the center, a decent angle, and suppose if we had enough graph paper, these two lines L1 and L2 would both land at my bright spot, but I don't have enough. I've got these gaps, my squiggles, to indicate that I need more graph paper. But so we're gonna kind of talk our way through this and see what we can see. All right, now critical. And this one ends at m equals 3. All right. So I'm not going to draw it in as ending up there, but we're going to say that it does. All right. Now, I'm going to draw in a red line segment, and I want you to watch how I do it. All right. I'm going to go to this. I'm actually going to use my protractor. I'll put on my glasses here. Boy, I hardly ever do this with a protractor. So this is going to be nice. Oops. It's going to be nice. All right. So I'm going to go to this dot and draw a 90-degree angle. Okay. Now, watch how I do this. I'm drawing a 90-degree angle from that upper dot in the center of the upper gap down to the L2 line. Okay. And in fact, let me draw it in red to emphasize it. Okay, so that line segment is perpendicular. I'll put a little right angle symbol here. Let me bring this in a little bit. All right. All right, now that forms a right triangle over here. Now I'm going to break that right triangle out. Okay. And so here's a miniaturized version of it, or an expanded, a magnified version of it. And actually, let me erase this one. I'll make that red. Okay, so here's my red line segment. And here is, okay, here's wavelet source number 2. Here's wavelet source number 1. So those are the 2 points up here in the gaps. All right. This angle here is theta, this acute angle here. This is a right angle over here. Okay. Right. Now let's label the other things that we know. This one here, this vertical line segment is D. That's the spacing of the slit. All right. So what we've done is we've taken this one, it's kind of small, so I space it out here to the right and down. But that distance between the 2 wavelet sources is D, so that's S2 to S1. And then here's my perpendicular line through S1. And then this one is actually L2 out here. And I'll just put dots. And then you can sketch dots out here for L1 if you want. All right, just to remind yourself of where they come from. Okay. Now I'm gonna erase this one so it doesn't get too cluttered up here. All right. All right. So now what is this? All right. What is this line segment right here from S2 to the right angle, to this vertex right here? Right. That's the critical thing. If you look at the diagram, both the waves, so here's a bunch of wave fronts going out. Okay. And from source number 1, here's a bunch of wave fronts. From source number 2, actually, let me make these about the same wavelength. Okay, so here's some from S2 or from S1, and here's some from S2. All right. Now they both land at B. They both end at M equals 3 bright spot. But here is the extra distance that the waves from S2 must travel. So this is delta L. Extra distance that waves from S2 must travel to the M equals 3 bright spot. All right. Now, if that distance is equal to lambda, your waves, by the time they get out here, are perfect. They're one wavelength behind. One perfect wavelength behind. So that means you have constructive interference. Okay, so if delta L is one wavelength, whatever your wavelength is, you get constructive interference at the bright spot. In fact, that defines the bright spot. Okay, the bright spot will only be at the angle at which you get delta L equals 1 lambda, or 2 lambda, or, and this is actually what we have, 3 lambda. Okay, this is ours. This is M equals 3. And guess what these other two are? These two, okay, this one, delta L equals lambda 1, that's this first bright spot here. All right, it doesn't, the angle's a little bit smaller, and you just have a smaller path difference. So this is what you would call the path difference. In general. All right. Yeah, question. Here? If delta L is 1 lambda, then you have constructive interference at the bright spot. All right. And then ditto for 2 lambda, and ditto for 3 lambda, and ditto on down, as many bright spots as you see. Okay. Now, if delta lambda is, or if delta L is half a wavelength, you get destructive interference out here. So let's call this a DS, a dark spot. That's the M equals 2 M equals 2 dark spot, and that corresponds to delta L equals 3 lambda over 2. All right. Now, right here at the symmetry line, that's the central bright spot. Okay, that's right here. Okay, that's M equals 0. Okay, and from the two, now think about this. From S1 and S2 here in the gaps, they both travel, no matter what the waves are doing, they travel the same distance to get to this one because it's symmetric. So you have the same right triangle from S2 to the symmetry spot as you do from S1 to the symmetry spot. But once you get off the axis, you break symmetry, and then you got to do this stuff up here. All right. So your basic, now let's look at this stuff here. Delta L is down here, and So basically, um, your condition is this. D, this is the hypotenuse, D times sine theta is equal to delta L. Okay? And I should make that delta lowercase l. All right? Now, we don't know what, we can't measure this because this is going to be in a few in a few hundred angstroms if it's visible light. All right? So we've got to make an approximation to that. All right? So what we want is constructive interference, bright spots. We want d sine theta equal to lambda over, or we want it to equal to a 1 lambda, 2 lambda, 3 lambda, dot, 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 all the way out to n lambda, or m lambda, I should say. Okay, so that's our constructive. This is your constructive interference condition. That's where you get a bright spot. All right. And then similar for lambda over 2, 3 lambda over 2 and stuff for your dark spots. All right. Now, how do you get theta? Well, the way to measure theta is basically to use this triangle. Now, I'm going to draw another triangle. It's a theta triangle, but it's a bigger one. And it's this one. Here's the right angle. Here's theta. This is L. And this is H. Okay? And so you can figure out, you can get all this stuff in here and figure out your L's and your H's and stuff. And you can this is how you would measure theta in the lab. So you can get everything in here. All right, from this one. And it's approximate. It's not exactly correct, but it's pretty close, pretty good enough for government work. All right. So your basic constructive, let me just reinforce, and I'll make it even bigger. D times the sine of theta equals m lambda for constructive interference. All right, so there's your nutshell. So these two are basically the same concept here. All right. And let me just go ahead and make a note. The slit distance, let me blow up my diagram a little bit here. Okay. The slit distance D down here is the design factor that this is how I design and manufacture my barrier with 2 gaps. Okay, so I designed this. I measure theta in the lab by doing H and L down here. And then I count this. I mean, M is just, counting 0, 1, 2, 3 above, or 0, 1, 2 down below, or whatever, whichever order it is. And from that, you can figure out lambda. All right, so let's do an example now. of some measurements that'll allow us to calculate the wavelength. Can you move my thing? Next slide. Good. Now we're going to do a calculation of a laser wavelength. And students, this is something that, do you think we can do we have diffraction gratings or anything? Do they have lasers? Do we have helium neon lasers in here? Go ask them how many helium neon, if we can use helium neon lasers. Okay, so here's an example. We're going to find a lasers with parentheses, wavelength. And then we're going to put them on sharks. Okay, so let's do another little dipsy diagram here. So here's my barrier. Here are my two gaps. Okay. And let's just draw a symmetry line out here. We're not going to draw that triangle in here. We're just going to do the measurements. And let's put our screen out here. So here's my perpendicular screen. If the screen's not perpendicular to symmetry line, you got a little bit more trig to do, but it's not too bodacious. Okay, so there's my screen, and it's perpendicular. And let me check my numbers here. So let's do, all right, I'm going to trace in. Okay, here's m equals 0, and m equals 1, m equals 2. I'm going to put my m equals 3. So this is my m equals 3 bright spot. Up here, okay? And so, and you measure, and let me do another line here out to my, and let's say that you do all of your trig, and you figure out that theta subscript 3 is 10.95 degrees. Okay. Now that sketch is a little bit bigger, but I'm blowing it up. We'll let the numbers do the talking here in a second. All right. And you get 10.95 from doing inverse tangent of, L and H over here. All right. Now, so this is a shorthand right here of this. And in actuality, these two scales these things are way out of scale, because this one, the spacing here has to be a very small fraction of a millimeter. But the distance here, L, in the lab is going to be meters. So that's many thousand times bigger than this thing. Now, on paper, this L segment here, in my original diagram, it looks about maybe 10 times D. But in reality, it's going to be thousands of times whatever my spacing here is. So we just have to let the numbers do the talking. And that's why this example, we're doing what we would call a shorthand for that previous diagram. Okay, now let's say that D, I'm still going to label D over here in my schematic. All right, let's just write down D equals 0.0 100 millimeters. All right. And so what is that in scientific notation? 0.01 times 0.001. Okay, let me switch to floating scientific. Okay. All right, that's 1 times 10 to the minus 5. 1.00. Yeah. Did you ask him if we have any
looking for helium neon, but he couldn't find specifically that. It said if you.
I'll talk to him after class. Never mind.
Okay.
Yeah, we might be able to use that here in a second. Yeah, okay, we'll use that in a few minutes. All right, so this is times 10 to the minus 5 meters. Okay, now our master equation is d sine theta subscript m equals m lambda for constructive. All right, so in this case, let's plug in our numbers now. 1.00 times 10 to the minus 5 meters times sine of theta 3, so that's 10.95 degrees, equals 3 lambda. All right, so I can figure out what my lambda is from this set of measurements. Right, this is my design. This is my measurement in the lab. And then this is this is also in the lab. You just count that. All right, so you can figure out lambda. All right, so go ahead and calculate lambda. Let's see if you get lambda by itself. Go ahead and calculate. And I'm going to start another question. And go ahead and refresh your calculator. And let's see if you can. Give me a number of nanometers to the nearest nanometer. All right, so take a few minutes to get lambda. All right, let's take a look at this. How do you turn this on over here? This thing turns it on? Oh, I see. Okay. Yeah, okay, good. Yeah, I can see a faint one over here. All right, so this one is 600, 300, 100. So this one here is the one that we're using right now. 100 lines per millimeter. Okay, so you could definitely get m equals 3. And we'll do that on one of the, we'll darken the room with that one. Now this one is,
So I'm gonna try to go home like today or tomorrow and fix my eye flicker. But if it doesn't, I mean I got them all wrong today, so it doesn't matter. But in the event that it doesn't work, would I be able to just write it down?
no, but give me my red pen.
The first 3 I got right. Oh, nice.
Yeah, so that's good. Yeah, you're just gonna have to miss today, but it's not, it's a mosquito bite.
Yeah, I'm gonna see if I can fix it when I go home. Like try to put up batteries or something. But
If you can't, see if you can borrow one off a friend.
and then just re-register it.
Yeah, and register it. Chris, could you come up here a minute? Kristen Collison.
But
Now you got a new iClicker several weeks ago, and then you re-registered it in web courses, right? And as soon as I synchronized, I got all your new data, right? So that's how it'll work for you,
So
Emily.
if I get a new one, I'll just like re-register and let you know.
Yeah, and you'll have 2 clicker ID numbers, but that's fine.
Okay, all right.
The software can handle that.
Okay, thanks.
What happened to Olivia?
She went to a new clicker.
Or what?
She went to another clicker, or like
She missed class. All right, so this one, so this is 0.0033. Okay, so this one's tighter. This one's, yeah, so this one's, the lambda's a lot bigger, so your diffraction pattern's spreading out quite a bit more. I gotta be careful with this, not to shine that in my eye. All right, let's turn this off. Yeah, that is primitive. I don't know why this is a total jury rig. UCF can be so stingy with money.
You might
All
have
right.
better ones.
What?
You might have better stuff if you tell them
Yeah,
specifically what you want, or what you're trying to do.
yeah, look at these answers. Okay, 30 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Um, raise your hand if you got 633 nanometers. Okay, that's the correct answer. 633 nanometers. Now, this is another one that this kind of a calculation would be good as a written problem and ask you to interpret this, or give you some kind of a design and ask you to figure out what's the wavelength that you're observing. Now, can you just keep it there, I guess. I'm going to do a demonstration up here, and I don't know if it's going to work very good. All right, go ahead and darken the room. All right, everybody take a look at this. All right, now I got a laser pointer up here, and I'm going to shine it over towards the door. All right, there it is. Now I'm going to try not to shine it in anybody's eyes. Okay. Now I'm going to put it down, turn it off, and I'm going to try to let's see. Can I borrow your notebook? I'm going to borrow Destiny's notebook and aim this thing up. Now, you guys turn away for a second. Let's see if we can get this. All right, there it is. All right, let me bring this back a little bit. All right, there it is, up on the wall. That's pretty good. Now, the other thing that I bring the lights up. The other thing I have up here is a fancy slide that has 3 different diffraction grades, kind of like the ones that we had on the first day of class that you could hold in your hand. This one's got 3 tiny ones. And go ahead and write down these separations. Separation number 1, 100 lines per millimeter. So what that means is D is equal to 1 millimeter divided by 100. All right. The second one, 300 lines per millimeter. Oh, by the way, the first one, 100 lines per millimeter, that's 1 millimeter divided by 100. That's 0.01 millimeters. That's what we just used in this calculation. There it is up there. D equals 0.0100 millimeters. Okay, that's the first one I got here. Next one, 300 lines per millimeter. So that's 1 millimeter divided by 300. All right, so that's 0.00333 millimeters per line, or D is equal to 0.0033 millimeters. The next one, this third one I've got is 600 lines per millimeter. So that's even smaller. 1 millimeter divided by 600. All right, now, let me ask you a question. For which of these is the wavelength, so it's green, right? So this is going to be about 500 or something. We can measure this wavelength if we want to. Do some, measurements, get theta, m lambda theta, or d sine theta equals m lambda. Got it. Right? So this is going to be 500 or something. Right? Now, which of these is the wavelength much smaller than the opening? In other words, which one has an opening that's a lot bigger than the wavelength? All right? Is it 100 lines per millimeter? Is it 300 lines per millimeter? Is it 600 lines per millimeter? Which one's got the biggest openings? The biggest D? 100. All right, now let's see. Now, oddly, if you have a big opening and a relatively short wavelength, the waves are just going to march right on through. All right, cut the lights. Let's start with 600. These are the tightest openings. All right, now here's my diffraction pattern. See it there? You see, I've got 2 dots. All right, now so mentally memorize that. All right, there's 300 lines per, so this is a little bit tighter, or a little bit bigger, I should say. This is the tightest. You get a good swing. And how many orders can you see? M equals 0, M equals 1. Anybody see M equals 2? Yeah, way over there to the right. And I don't see one over to the left, but, oh, is it? Okay. Now this is 300 lines. Let's see, I got M equals 3 over there. Very dim. And yeah, this thing's kind of tilty a little bit. Let's see if I can do this. There we go. Yeah, so we got oh yeah, there's that other one. Right? So this is a tighter diffraction pattern. Now here's 100, the biggest opening, and look how it tightens up. Now we still get a visible diffraction pattern here. All right? But boy, we got a lot of orders. We got a lot of orders here. Okay, my central is right above the fuse box. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I got 11 orders left, and not quite that many on the right. I got to tilt maybe this is kind of impromptu, so I'm not getting the perfect alignment. It's not perfectly straight stuff, but now, if I went to 50 lines per millimeter, D is even bigger. My diffraction pattern would tighten up. Now, I'm going to use a very primitive diffraction device. It's called the right-hand rule. See, look at this. See this? See this? This is my opening right here. Let's see how tight the pattern is. Dun, 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 dun. They go all the way through. They do not diffract because this is way, way too big compared to the wavelength. All right? So let's review. Fairly close to the wavelength, medium close to the wavelength, furthest from the wavelength, and way, way bigger. No diffraction at all. All right, so this is like about 50 millimeters here, so quite a bit bigger. All right, that my wonderful student. Now that's a diffraction grating. It's not a double slit. It's a diffraction grating, but it's wave interference, and we get the same similar effects. Now bring the lights up, and let me. Oh, you could take this gear back to Ray. I want to go through. Oh boy. We're going to go through and do a single slit diffraction. Let's see if I can. There we go. All right, now we're going to do another sketch. This one's going to be a little bit different because single slit is a little bit different geometry than double slit. So we can handle it. All right, so here we go. Single slit diffraction. Example. All right, now this one, I'm going to draw my barrier over here. I'm going to make it a little thinner so that my sketch is, oh, wait a minute, that's two slits. That's all right. Let me just, okay, there's one slit. Okay, let me make the, did you tell Ray thank you? All right, so here's my opening. All right, and then I'm gonna pound some plane waves through here at about the same wavelength. So here's some plane waves going in. All right. And the width, now the factor here, the design factor here is W, the width of the slit. All right. And again, we're going to draw a symmetry line through the middle. So kind of draw that. And we're going to put a gap in it again. And a squiggle to indicate, you know, how far it really is away. I'm going to put my screen out here at right angles to it. All right. And let me put in some hatching here to indicate that it's a solid object. And same thing over here with my slits or my barriers. So this is like a door. Now in real life, our doors, you know what, that is significant. What are you researching? Asteroids. You know, one of the things that we're doing at UCF, we're trying to figure out quantum electronics. And that, my wonderful students, is a gate, a door. And your electronics, your devices, your transistors and stuff, the logic is everything is logical in a computer. It follows rules of logic. And the way they do that is with electronic gates. But this would be optical at the speed of light. I'm going to have to think about this. Anyways, let's get back to the reality, not la la land here. All right. So this is m equals 0, right? Okay, that one's always bright, no matter what happens. And let's put a single dot here to represent a source, a wavelet source in the gap. All right. And let's go up here, a distance y. And let's make this a dark spot up here. All right. A distance y, and of course, this is L again, down here, a few meters. You know, if it's on your desktop, it could be half a meter. Okay. And so let's say that, let's take a look at our calculations here. So let's say that this one is, let's maybe check my things here. All right. From the first edge and the second edge, draw some lines with squigglies. And I'm not going to connect either of them, but they keep going out to the dark spot. Okay. So let's say that y is equal to, let's say that L is equal to 0.40 meters. Okay. And let's say that lambda is 410 nanometers. All right. Now my path difference triangle is going to look similar again. Okay. Now I'm not going to draw it in over here with inside my barriers, but I am going to draw it over here to the side, and I'll make this perpendicular side red as before. Okay, so there's my path difference triangle. Okay, so this is delta L, right? Or delta lowercase l, I should say. And this is W. Okay. Now, if this is equal to lambda, then the sine of this theta is equal to lambda over W. Okay. Now, let's put in our lambda, 410 nanometers. And our W, let's say that our W is, I'll write it over here, 5 times 10 to the minus 6 meters. So it's 5 microns. Okay. So we'll write it down here, 5 times 10 to the minus 6 meters. And actually this is 410 times 10 to the minus 9 meters divided by 5 times 10 to the minus 6 meters. So meters and meters cancel. I've got 410 over 5 is 82. So this is equal to 82 times 10 to the minus 3. Right? So that's equal to 0.082. That's the sine of theta. All right. And so theta, let's figure this out. So the sine of theta is equal to 0.082. So what do you get for theta? It's going to be pretty small. 0.7? 4.7? Anybody verify that? Okay, 4.7 degrees. Okay, so this is pretty close. Right? It's really tight. And you know, in my diagram here, I don't know, I've got about 30 degrees up here for theta. But you know, when they let the numbers do the talking, then you can figure out the exact angle here. All right. So now let's figure out why. All right. Now, here's my big laboratory triangle. This is my triangle of wavelengths, my triangle of light paths. This was my triangle in the lab, so this is my lab triangle. So this is L, this is Y, and this is 4.7 dineros down here. So, and this is 0.040 meters here. So Y is equal to, all right, you got to use a tangent of theta. So Y is equal to 0.40 meters times the tangent of 4.7 degrees, which is what? It's going to be pretty small. It's a small angle. It's going to be a small distance. Who's got a distance from this? Okay, that's what I got, 0.033 meters. Now, here's the interesting thing. These things, and so that's your dark spot location, all right? Now, if you decrease the width of the opening, you'll expand the fringe. You'll expand the pattern, just like we mentioned with the green laser. So if you expand, if you increase W, no, if you decrease W, let's do it that way. If you decrease W, you expand the pattern in general. So you could do this again with a different W up here, you know, like, 2.5 microns, and you get a slightly different numbers out here. Okay, and the pattern will change. All right. Now, this is all in chapter 27. So I want you to, can you switch over to the laptop, please? Okay. All right, this is chapter 27. And so we just did the single slit diffraction grading. Now I'm going to give you some more work with diffraction on Friday, but I want you to start skimming ahead. We're going to dismiss a little early today. That's all right. If you want to stay after and talk to me about grades, you can. Start skimming ahead into chapter 29.6. So skip over chapter 28 and into 29, and then just check and just skim, because I'm going to hit it very, very lightly in chapter 29. And we already did something in 29, polarization. Okay, you're dismissed. Let's shut this down.